From comic book heroes to sci-fi movies, nuclear radiation is often the key to incredible transformations and dramatic dangers. That's radiation that results from the breakdown of atomic nuclei. But what makes an atomic nucleus radioactive in the first place? Why are some nuclei stable while others decay? Let's dive into the nucleus and explore what's really going on inside radioactive isotopes. This is Real Chem. In chemistry, we usually focus on electrons because it's the interactions of electrons that dominate most chemical reactions. But the nucleus, the heart of the atom, can sometimes drive some really unique chemistry. How does that work? Well, not all nuclei are created equal. Some are really stable, while others will inevitably decay, transforming into different elements and subatomic particles. What determines which nuclei are stable and which are not? It all comes down to the delicate balance between protons and neutrons. Let's take a closer look at what tips the scales between stability and radioactivity. Before we dive in, let's take a moment to review isotopic notation and explore it more deeply than we usually do. You've seen this before. An isotope is represented with the atomic symbol in the center, the mass number on the upper left, and the atomic number on the lower left. This notation is useful when considering the atom from the outside. But now that we're diving into the nucleus, we're going to adjust our language. Instead of calling the top number the mass number, we'll refer to it as the total number of particles in the nucleus, protons and neutrons. Since these particles have nearly the same mass, total number and mass number are simply two ways of describing the same concept. And instead of atomic number, we'll refer to the lower number as the total number of protons in the nucleus, which also represents the nucleus's total charge, since only protons carry charge while neutrons remain neutral. Equipped with this way of thinking and talking about the nucleus, we're ready to understand stable versus radioactive nuclei. First, consider this. Nearly all atomic nuclei are made of two or more positively charged protons. Since charges repel, why don't all the atomic nuclei just fly apart? You might think it has to do with negative charges, with electrons. But there aren't any electrons or other particles with negative charges in the nucleus. Electrons are all far outside the nucleus. It turns out the neutrons help stabilize atomic nuclei, not through electrical Coulomb forces, but via the strong nuclear force, an immensely powerful force that binds neutrons and protons together, counteracting the repulsion between positive charges in a tiny space. The stability of any particular atomic nucleus depends on the balance between the number of protons and the number of neutrons. For a given element with a specific atomic number, or proton number, multiple isotopes can exist, differing only in their neutron count. For example, all nuclei of the element carbon have 6 protons, but the number of neutrons can vary. Most carbon on Earth is carbon-12, which has 6 neutrons to go with 6 protons. But there's also carbon-13. That's an isotope of carbon with 7 neutrons instead of 6. Both carbon-12 and carbon-13 are stable isotopes of carbon. Those nuclei don't decay. But carbon-14, which has 8 neutrons to go with 6 protons, is an important isotope. It's unstable. It decays. A pile of carbon-14 atoms would decay by half its amount in approximately 5,730 years. Add another neutron and we have carbon-15. It's much less stable than carbon-14. If that same pile of carbon was made of carbon-15, half of it would be gone in only 2.4 seconds. So isotopes of carbon that have more than 7 neutrons are unstable. It turns out the same is true of carbon isotopes that have less than 6 neutrons. Carbon-10 and carbon-8 are also unstable. For carbon, there's a sweet spot when it comes to the number of neutrons. Isotopes with 6 or 7 neutrons are in the stable zone. Now, if we expand our view beyond carbon and look at all the elements, we see a similar pattern. Each element has its own sweet spot, the zone where there aren't too few or too many neutrons to hold its nucleus together. To organize our thoughts about this, we can make a chart with the number of protons on the x-axis, representing different elements, and the number of neutrons on the y-axis. On that chart, we can map out all the isotopes that have ever been observed. Chemists call this the chart of the nuclides. Each point on the chart represents a nucleus, with colors differentiating stable isotopes from radioactive ones. These stable isotopes form a diagonal line, the valley of stability. Nuclei in the valley have a balanced proton to neutron ratio, while those outside the valley are unstable and decay over time. If we zoom in on the valley of stability, we can use the chart to help predict nuclear decay processes. For example, carbon-14, with 6 protons and 8 neutrons, lies just above the stable region. It has more neutrons than the ideal balance, and so to restore balance, a neutron decays into a proton and electron. That reduces the neutron count to 7 and increases the proton count to 7. Changing the proton count changes the atomic number and hence the element. So now we have nitrogen instead of carbon with a mass of 14, which sits in the valley of stability. In general, nuclei that lie above the valley have too many neutrons relative to protons. These will decay through processes that decrease the neutron to proton ratio, moving them closer to or into the valley of stability. On the other hand, nuclei below the valley have too few neutrons relative to protons. These will decay through processes that increase the neutron to proton ratio. There's one other area on the chart of the nuclides. At the upper end of the graph, where nuclei contain a large amount of protons and neutrons, the strong nuclear force can no longer hold everything together. These nuclei are all radioactive. They decay in ways that send them diagonally down into the valley. Nuclear reactions are very different from chemical reactions, but they're similar in one important way. The products of the reaction are always more stable than what we started with. Whether in the lab or in nature, everything works its way toward the most stable state. Once we understand the science, we can harness nuclear reactions for our benefit, like certain kinds of medical imaging that save lives. Despite what sci-fi might suggest, nuclear stability isn't about superpowers. It's just good science.